Hello. We're going to be reading one more story. It'll take me two lessons to read it, and then we will compare all three of them. And that will be the end of ELA for the school year. I hope you enjoy this last book. It's called A Black Hole is Not a Hole. Then what is it? By Carolyn Simani Di Cristofano, illustrated by Michael Carroll. A black hole is not a hole, at least not the kind you can dig in the ground or poke your finger through. You can't just walk along and fall into one. A black hole isn't a hole like that. If a black hole is not a hole, then what in the universe is it? Places with pull. A black hole is a place in space with a powerful pull. Way out beyond where you are right now, beyond the clouds, beyond the moon, beyond Pluto, beyond our solar system, space goes on and on. You could travel for trillions of miles and you'd barely get to the closest star. In another few trillion miles, you might pass another star. Space is that huge. Way out there, trillions, quadrillions, and even more illions of miles away, there are special places called black holes. These places in space are special because of their powerful pull on other things. A black hole's pull is the strongest pull in the entire universe. Nothing can out-tug a black hole. No army of tow trucks, no convoy of supersized earth haulers, no fleet of giant rocket engines. Not all of them combined. A black hole pulls in nearby dust. It pulls in nearby asteroids, it pulls in nearby stars, and even nearby starlight. And no light, stars, asteroids, or dust come out. Not ever. A black hole is like a giant whirlpool. Have you ever pulled out a sink stopper and watched water swirl down the drain? Spirals of water flow toward the center. You've made a small whirlpool. Imagine a bigger whirlpool in a river. Far away, nobody knows it's there. Boats chug and sail along. Schools of fish dart by, following their fishy urges. Closer to the whirlpool, it's a different story. A fish swimming near the whirlpool's edge feels a gentle tug as the current drags it toward the spinning center. No problem. With a little swish, the fish can speed up, give itself enough oomph to swim away. After putting some distance between itself and the whirlpool, the fish no longer feels the current's inward pull. But what if the fish drifted further in? Closer to the center of the whirlpool, the pull would grow stronger. To escape the whirlpool, the fish would have to swim faster than it had to at the edge. Even closer to the middle, if the fish couldn't go much faster, it would find itself swept all the way in, stuck in the swirl, pulled round and round and round. A black hole works something like a whirlpool. Even though a black hole's pull is the strongest in the universe, it's not strong from far away. Galaxies and stardust drifting through space don't get dragged into a distant black hole. However, near a black hole, gases and dust and stars encounter its tug. Some things may be hurtling by so fast they won't get pulled into the black hole. Other things may not be as swift. They will be drawn in. Closer and closer, the tugging force gets stronger and stronger. Close enough, the black hole no longer acts like a whirlpool. What a drag. The caption under the picture says, "The inward pull of swirling whirlpool gets stronger near its center. The closer a fish gets, the closer a fish or anything else gets to the center, the more speed it needs to get out." Even though it's like a whirlpool, a black hole is not a whirlpool. With a whirlpool, there's always a fast enough fish or fast enough something that moves so quickly it won't be pulled in all the way into the center. Not so with a black hole. Within a certain distance, the black hole's power is so strong, nothing is fast enough to zip away. This is a black hole's special trait, its super pulling zone. Outside the zone, there's always the chance that something will zoom past and away, but anything inside this zone stays in the black hole's place in space forever. Nothing else in the universe is so inescapable. So a black hole is not a whirlpool, just sort of acts like one. There's another difference. In a whirlpool, the swirling current of water draws the fish into the center, But a black hole isn't made of water. Something else drives its pulling power. The caption for the picture there says, like a fish caught in a whirlpool, colorful glowing gases swirl toward a black hole. The dark center makes the black hole's super pulling zone. Artist's representation. That means that's what they think the artist who drew it thinks it looks like. The pulling power of a black hole. A black hole is an extreme gravity zone. Gravity is the source of a black hole's super pull. You deal with gravity every day. You count on it to bring you back to the ground when you jump up. You depend on it when you try to catch a pop fly, knowing the ball will fall down. You expect it to be there, even if you don't think about it much. People must have always noticed that objects fall, but they didn't know what made this happen. They certainly didn't guess that falling objects had anything to do with the stars, moons, planets, and sun. But then one man came along with new ideas. Gravity rules. That man was Isaac Newton. In 1687, he proposed that objects fall to the ground because Earth pulls on them. But his idea reached beyond Earth. He suggested that all things pull on each other, even when they are not touching. He considered this pull a force of nature and referred to it as gravitas, we now call gravity. The caption there says, just outside a black hole's extreme gravity zone is its gravitation is still remarkable. In this artist's picture, a black hole pulls a cloud of gas off a nearby star. And then there's a picture, a drawing of Isaac Newton and his apple. An extreme case of gravity. Remember that super pulling space around a black hole, the one with the strongest pull in the universe? That super pull is the close up gravitational power of a black hole. Here, in this zone, the gravity is so intense that nothing can move fast enough to fly, launch, jump, or zoom away. Around its extreme zone is a boundary called the event horizon. This boundary acts like a point of no return. Once past it, there is no going back. Only black holes have such extreme gravity zones, and only black holes have event horizons. This is what makes a black hole different from everything else. But a black hole is more than just a gravity zone, more than just empty space inside an event horizon. A black hole also includes the source of its tremendous gravitation, a massive amount of densely packed matter sitting at its center. The matter is so densely packed that it forms a single point called a singularity. Where does this matter come from? How did it get to be so densely packed? And what does it have to do with the beginning of a black hole? The answer lies in the stars. The caption for the picture says, this cross-section diagram shows the anatomy of a black hole. At the center is an extremely small, densely packed singularity, super enlarged for visibility. Surrounding the singularity is an extreme gravity zone, colored red. The outer boundary of this zone is the event horizon. Diagram is not to scale. Inside the orange text box, it says, an event? What? Have you ever watched the sunset? After it sinks below the horizon, Earth blocks your view of it. Even though you know it's still out there in space, you can't see it. Any and all events on the sun remain invisible to you for as long as it's below the horizon. If the sun suddenly turned purple, you wouldn't see it happen. In a similar way, once an object enters the extreme gravity zone of a black hole, the object disappears from view. Even though nothing physically blocks our sight, once the object is beyond the boundary of the zone, we cannot see what happens to it. Events beyond the black hole's horizon are invisible to us. Because of this visual effect, scientists named the boundary zone the event zone. And then that small text bubble says, what happens below the horizon stays below the horizon. Black hole beginnings. The beginning of a black hole can be the end of something else. Black holes come from stars. Every star has a beginning, when light first bursts from it. Then it shines on and on for millions, even billions of years, but every star comes to an end. And sometimes a star's final moments are an all-out frenzy. After the dust clears, a black hole may be all that's left. Black hole's first picture. Aww. Star power. Before a star, it is an enormous cloud of gases. At the start, wisps of gas drift off, drifts of dust collect. Their gravities At the start, wisps of gas and drifts of dust collect, their gravity drawing them together. As more stuff gathers, its combined gravitation grows stronger. Eventually, the cloud pulls itself into a massive ball of material. Under the force of its own weight, the gigantic ball presses inward. Deep beneath the surface, the intense pressure squeezes the material like the powerful grip of a giant hand. The inner material packs together tightly. More matter mounts up on the outside, increasing the pressure on the inside. Soon the pressure in the center is so high it ignites a booming nuclear reaction. Starlight bursts from the ball of gas, now blazing, flaring, spewing, and spouting. The new star is a fiery furnace, sparking a star. A star's fiery nuclear reaction is not really a fire. Instead, it is a dramatic melding or blending of atoms called nuclear fusion. Each atom has its own tiny center or nucleus. Surrounding each nucleus is an electrical force field. Ordinarily, this force field repels other nuclei, pushing them away. But in a star, the nuclei meld. How come? As the star materials gather, its inward pressure grows. The nuclei respond by zipping and zooming faster and faster, veering away from each other all the while. However, when the pressure gets high enough, the nuclei are going so fast that their speed overpowers their repulsion. Slamming into one another, they push through each other's force fields and fuse. As the nuclei meld, a smidgen of their matter vaporizes into energy. This creates a tremendous burst of furious noise, motion, and another byproduct, starshine. In the star's center, the gas is so energized that it has become sort of a super gas called plasma. The hot plasma is in constant motion. It expands like hot air inside a balloon and pushes outward from the center. Meanwhile, the crushing weight of the star material continues to press inward. In goes the outer material and out goes the inner. The plasma rolls and churns like a hyper hurricane of heat, light, sound, and motion. The star ball holds together in this perfectly balanced commotion for millions or billions of years until the star's nuclear furnace runs out of fuel. The reaction suddenly ceases. When that happens, look out, the end of the star is near. The caption on page 42 says, like other stars, the sun is a blazing ball of activity. As the brightest and hottest material rolls and swirls, darker, less hot material sinks toward the center. The flare in the upper right is a tremendous whip of plasma lashing out into space. False, color telescope image. So it's from a telescope. Out of fuel, out of time. This is a blast! Some stars go out in a blaze of glory. Once the nuclear reaction stops, the star's center begins to cool. The plasma slows down, its outward pushing growing weak. The balance is broken. The plasma collapses on itself. In one giant sudden whoosh, the center of the star compresses. It caves in, growing denser and tighter than ever. Crash! This core material bumps hard against itself. Boom! The material rebounds like an ocean wave slamming against a rock cliff. It pushes on the star's outer gases, which flow outward in giant surges of heat and light, and the star material rushes outward. The star grows and grows until it is a supernova or superstar. What happens next? Possibly a black hole forms. Possibly not. In this artist's illustration, a massive star comes to a spectacular end, its gases rebounding from the dense center and surging outward in bursts of light, heat, and motion. It all depends on the original mass of the star. If the star was about 25 to 40 times the size of our sun, then what's left of the star's center goes into a sudden collapse called fallback. Once again, the star stuff plunges inward under its own weight. In it pulls Tighter and tighter, the material contracts, crunching in so fast and so hard that it is destroyed. Even its atoms are utterly demolished. All of the matter that once filled the center of the star shrinks down to a single tiny point of extremely dense mass. It has no recognizable parts, but it does have one feature that makes it unique. It has a pull of gravity so strong that it can outpull anything else in the universe. Nothing can outtug it. No army of tow trucks, no convoy of supersized earth haulers, no fleet of giant rocket engines, not all of them combined. Do you recognize this pull? It's the pull of a black hole. The star, a big, brilliant ball of light, has turned into a dark place of enormous gravitation. A black hole has formed. The caption to the picture says, in 1987, a distant star appeared as a pinpoint in the before picture before bursting out as a brilliant supernova in the aftershot. And I'm going to stop there for today. Go give those questions a good try. Good luck.